Fat Man was the code name for the type of atomic bomb that was detonated over the Japanese city of Nagasaki by the United States on 9 August 1945. It was the second of the only two nuclear weapons ever used in warfare, the first being Little Boy, and its detonation caused the third man-made nuclear explosion. It was built by scientists and engineers at Los Alamos Laboratory using plutonium from the Hanford site and dropped from the Boeing B-29 Superfortress bomb car. For the Fat Man mission, bomb car was piloted by Major Charles W. Sweeney. The name Fat Man refers generically to the early design of the bomb, because it had a wide, round shape. It was also known as the Mark III. Fat Man was an implosion-type nuclear weapon with a plutonium core. The first of that type to be detonated was the Gadget, in the Trinity nuclear test. Less than a month earlier, on 16 July, at the Alamogordo bombing and gunnery range in New Mexico, two more Fat Man bombs were detonated during the Operation Crossroads nuclear tests at Bikini Atoll in 1946. Some 120 Fat Man units were produced between 1947 and 1949, when it was superseded by the Mark Chapter 4 nuclear bomb. The Fat Man was retired in 1950. Early decisions. In 1942, prior to the Army taking over wartime atomic research, Robert Oppenheimer held conferences in Chicago in June and Berkeley, California, in July, at which various engineers and physicists discussed nuclear bomb design issues. A gun-type design was chosen, in which two subcritical masses would be brought together by firing a bullet into a target. The idea of an implosion-type nuclear weapon was suggested by Richard Tolman but attracted scant consideration. The feasibility of a plutonium bomb was questioned in 1942. James Conant heard on 14 November from Wallace Akers, the director of the British Tube Alloys project, that James Chadwick had concluded that plutonium might not be a practical fissionable material for weapons because of impurities. Conant consulted Ernest Lawrence and Arthur Compton, who acknowledged that their scientists at Berkeley and Chicago respectively knew about the problem, but could offer no ready solution. Conant informed the director of the Manhattan Project, Brigadier General Leslie R. Groves, Jr., who in turn assembled a special committee consisting of Lawrence, Compton, Oppenheimer and Macmillan to examine the issue. The committee concluded that any problems could be overcome simply by requiring higher purity. Oppenheimer, reviewing his options in early 1943, gave priority to the gun-type weapon, but as a hedge against the threat of pre-detonation, he created the E5 group at the Los Alamos Laboratory under Seth Neddermeyer to investigate implosion. Implosion-type bombs were determined to be significantly more efficient in terms of explosive yield per unit mass of fissile material in the bomb, because compressed fissile materials react more rapidly and therefore more completely. Nonetheless, it was decided that the plutonium gun would receive the bulk of the research effort. Since it was the project with the least amount of uncertainty involved, it was assumed that the uranium gun-type bomb could be easily adapted from it. Naming the gun-type and implosion-type designs were codenamed Thin Man and Fat Man, respectively. These codenames were created by Robert Serber, a former student of Oppenheimer's who worked on the Manhattan Project. He chose them based on their design shapes. The Thin Man would be a very long device, and the name came from the Dashiell L. Hammett detective novel The Thin Man and series of movies by the same name. The Fat Man would be round and fat, and was named after Sidney Greenstreet's character in The Maltese Falcon. Little Boy would come last and was named after Alicia Cook, Jr.'s character in the same film, as referred to by Humphrey Bogart. Development. Neddermeyer discarded Serber and Tolman's initial concept of implosion as assembling a series of pieces in favor of one in which a hollow sphere was imploded by an explosive shell. He was assisted in this work by Hugh Bradner, Charles Critchfield, and John Stribe. Lt.E. Thomson was brought in as a consultant, and discussed the problem with Neddermeyer in June 1943. Thomson was skeptical that an implosion could be made sufficiently symmetric. Oppenheimer arranged for Neddermeyer and Edwin Macmillan to visit the National Defense Research Committee's Explosives Research Laboratory near the laboratories of the Bureau of Mines in Bruceton, Pennsylvania, where they spoke to George Kistiakowsky and his team. But Neddermeyer's efforts in July and August at imploding tubes to produce cylinders tended to produce objects that resembled rocks. Neddermeyer was the only person who believed that implosion was practical, and only his enthusiasm kept the project alive. Oppenheimer brought John von Neumann to Los Alamos in September 1943 to look at implosion with a fresh set of eyes. After reviewing Neddermeyer's studies, and discussing the matter with Edward Teller, von Neumann suggested the use of high explosives in shaped charges to implode a sphere, which he showed could not only result in a faster assembly of fissile material than was possible with the gun method, but which could greatly reduce the amount of material required, because of the resulting higher density. The idea that, under such pressures, the plutonium metal itself would be compressed came from Teller, whose knowledge of how dense metals behaved under heavy pressure was influenced by his pre-war theoretical studies of the Earth's core with George Gamow. The prospect of more efficient nuclear weapons impressed Oppenheimer, Teller and Hans Bethe, but they decided that an expert on explosives would be required. Kistiakowsky's name was immediately suggested, and Kistiakowsky was brought into the project as a consultant in October 1943. The implosion project remained a backup until April 1944, when experiments by Emilio G. Segre and his P5 group at Los Alamos on the newly reactor-produced plutonium from the X-10 graphite reactor at Oak Ridge and the B reactor at the Hanford site showed that it contained impurities in the form of the isotope plutonium-240. This has a far higher spontaneous fission rate and radioactivity than plutonium-239. The cyclotron-produced isotopes, on which the original measurements had been made, held much lower traces of plutonium-240. Its inclusion in reactor-bred plutonium appeared unavoidable. This meant that the spontaneous fission rate of the reactor plutonium was so high that it would be highly likely that it would pre-detonate and blow itself apart during the initial formation of a critical mass. The distance required to accelerate the plutonium to speeds where pre-detonation would be less likely would need a gun barrel too long for any existing or planned bomber. The only way to use plutonium in a workable bomb was therefore implosion. The impracticability of a gun-type bomb using plutonium was agreed at a meeting in Los Alamos on 17 July 1944. All gun-type work in the Manhattan Project was directed at the Little Boy enriched uranium gun design, and the Los Alamos laboratory was reorganized, with almost all of the research oriented around the problems of the implosion for the Fat Man bomb. The idea of using shaped charges as three-dimensional explosive lenses came from James L. Tuck, and was developed by von Neumann. To overcome the difficulty of synchronizing multiple detonations, Luis Alvarez and Lawrence Johnston invented exploding bridge wire detonators to replace the less precise primer core detonation system. Robert Christie is credited with doing the calculations that showed how a solid subcritical sphere of plutonium could be compressed to a critical state, greatly simplifying the task, since earlier efforts had attempted the more difficult compression of a hollow spherical shell. After Christie's report, the solid plutonium core weapon was referred to as the Christie gadget. The task of the metallurgists was to determine how to cast plutonium into a sphere. The difficulties became apparent when attempts to measure the density of plutonium gave inconsistent results. At first, contamination was believed to be the cause, but it was soon determined that there were multiple allotropes of plutonium. The brittle alpha phase that exists at room temperature changes to the plastic beta phase at higher temperatures. Attention then shifted to the even more malleable delta phase that normally exists in the 300 to 450 degrees Celsius range. It was found that this was stable at room temperature when alloyed with aluminum, but aluminum emits neutrons when bombarded with alpha particles, which would exacerbate the pre-ignition problem. The metallurgists then hit upon a plutonium-gallium alloy, which stabilized the delta phase and could be hot-pressed into the desired spherical shape. As plutonium was found to corrode readily, the sphere was coated with nickel. The size of the bomb was constrained by the available aircraft. The only Allied aircraft capable of carrying the Fat Man were the British Avro Lancaster and the American Boeing B-29 Superfortress. For logistic and nationalistic reasons, the B-29 was preferred, but this constrained the bomb to a maximum length of 132 inches, width of 60 inches and weight of 20,000 pounds. Removing the bomb rails allowed a maximum width of 66 inches. Drop tests began in March 1944, and resulted in modifications to the silver plate aircraft due to the weight of the bomb. High-speed photographs revealed that the tail fins folded under the pressure, resulting in an erratic descent. Various combinations of stabilizer boxes and fins were tested on the Fat Man shape to eliminate its persistent wobble until an arrangement dubbed a California parachute. A cubical open rear tail box outer surface with 8 radial fins inside of it, 4 angled at 45 degrees and 4 orthogonally to the line of fall holding the outer square fin box to the bomb's rear end, was approved. In drop tests in early weeks, the Fat Man missed its target by an average of 1,857 feet, but this was halved by June as the bombardiers became more proficient with it. The early Y-1222 model Fat Man was assembled with some 1,500 bolts. This was superseded by the Y-1291 design in December 1944. This redesign work was substantial, and only the Y-1222 tail design was retained. Later versions included the Y-1560, which had 72 detonators, the Y-1561, which had 32, and the Y-1562, which had 132. There was also the Y-1563 and Y-1564, which were practice bombs with no detonators at all. The final wartime Y-1561 design was assembled with just 90 bolts. Because of its complicated firing mechanism, and the need for previously untested synchronization of explosives and precision design, it was thought that a full test of the concept was needed before the scientists and military representatives could be confident it would perform correctly under combat conditions. On 16 July 1945, a Y-1561 model Fat Man, known as the Gadget for security reasons, was detonated in a test explosion at a remote site in New Mexico. Known as the Trinity test, it gave a yield of about 20 kilotons. Some minor changes were made to the design as a result of the Trinity test. Philip Morrison recalled that there were some changes of importance. The fundamental thing was, of course, very much the same: bomb interior. The bomb was 128 inches long and 60 inches in diameter. It weighed 10,300 pounds. Assembly. To allow insertion of the 3.62-inch diameter plutonium pit, containing the 0.8-INCH diameter, Urchin, modulated neutron initiator, as late as possible in the device's assembly. The spherical 8.75-inch diameter depleted uranium tamper surrounded by a 0.125-inch thick shell of boron-impregnated plastic had a 5-inch diameter cylindrical hole running through it, like the hole in a quad apple. The missing tamper cylinder, containing the pit, could be slipped in through a hole in the surrounding 18.5-INCH diameter aluminium pusher. The pit was warm to touch, emitting 2.4 W per kilogram Pu, about 15 W for the 6.19 kilograms core. The plutonium was compressed to twice its normal density before the Urchin added free neutrons to initiate a fission chain reaction. An exploding bridge wire detonator simultaneously starts a detonation wave in each of the 32 tapered high explosive columns. The detonation wave is initially convex in the faster explosive. The wavefronts become concave in the slower explosive. The 32 waves then merge into a single spherical implosive shock wave which hits the inner charge's faster explosive. The medium-density aluminium pusher transfers the imploding shock wave from the low-density explosive to the high-density uranium, minimizing undesirable turbulence. The shock wave then compresses the inner components, passing through a boron plastic shell intended to prevent pre-detonation of the bomb by stray neutrons. The shock wave reaches the center of the bomb, where the beryllium-210 polonium Urchin is crushed, pushing the two metals together and thereby releasing a burst of neutrons into the compressed dot pit of the nickel-plated delta phase alloy of 239 plutonium-240 plutonium-gallium. A fission chain reaction then begins. The tendency of the fissioning pit to blow itself apart prematurely is reduced by the inward momentum of the natural uranium tamper. The tamper also reflects neutrons back into the pit, accelerating the chain reaction. When sufficient fast neutrons are produced, the tamper itself undergoes fission, accounting for up to 20% of the weapon's yield. The result was the fission of about 1 kilogram of the 6.19 kilograms of plutonium in the pit, i.e., of about 17% of the fissile material present. 1 gram of matter in the bomb is converted into the active energy of heat and radiation, releasing the energy equivalent to the detonation of 21 kilotons of TNT or 88 terajoules. Bombing of Nagasaki. The first plutonium core, along with its polonium-beryllium Urchin initiator, was transported in the custody of Project Alberta courier Rima Schreiber in a magnesium field carrying case designed for the purpose by Philip Morrison. Magnesium was chosen because it does not act as a tamper. The core departed from Kirtland Army Airfield on a C-54 transport aircraft of the 509th Composite Group's 320th Troop Carrier Squadron on the 26th of July, and arrived at Northfield on Tinian on the 28th of July. 3 Fat Man high-explosive pre-assemblies, designated F-31, F-32, and F-33, were picked up at Kirtland on the 28th of July by 3 B-29S-2. Luke the Spook-and-Lagan Dragon, from the 509th Composite Group's 393d Bombardment Squadron +1 from the 216th AAF Base Unit, and transported to Northfield, arriving on the 2nd of August. Upon arrival, F-31 was partly disassembled in order to check all its components. F-33 was expended near Tinian during a final rehearsal on the 8th of August, and F-31 was the bomb dropped on Nagasaki. F-32 presumably would have been used for a third attack or its rehearsal. In August 1945, the Fat Man was assembled on Tinian by Project Alberta personnel. When the physics package was fully assembled and wired, it was placed inside its ellipsoidal aerodynamic bomb shell and wheeled out, where it was signed by nearly 60 people, including Rear Admiral William R. Purnell, Brigadier General Thomas F. Farrell and Captain William S. Parsons. It was then wheeled to the bomb bay of the B-29 superfortress named Bockcar after its normally assigned command pilot, Captain Frederick C. Bock, who flew the Great Artiste with his crew on the mission. Bockcar was flown by Major Charles W. Sweeney and his crew, with Commander Frederick L. Ashworth from Project Alberta as the weaponeer in charge of the bomb. Bockcar lifted off at 3:47 on the morning of the 9th of August 1945, with Kokura as the primary target and Nagasaki the secondary target. The weapon was already armed, but with the green electrical safety plugs still engaged. Ashworth changed them to red after 10 minutes so that Sweeney could climb to 17,000 feet in order to get above storm clouds. During pre-flight inspection of Botkar, the flight engineer notified Sweeney that an inoperative fuel transfer pump made it impossible to use 640 US gallons of fuel carried in a reserve tank. This fuel would still have to be carried all the way to Japan and back, consuming still more fuel. Replacing the pump would take hours. Moving the Fat Man to another aircraft might take just as long and was dangerous as well, as the bomb was live. 509th Composite Group Commander Colonel Paul Tibbets and Sweeney therefore elected to have Botkar continue the mission. The original target for the bomb was the city of Kokura, but it was found to be obscured by clouds and drifting smoke from fires started by a major firebombing raid by 224 B-29s on nearby Iwata the previous day. This covered 70% of the area over Kokura, obscuring the aiming point. 3 bomb runs were made over the next 50 minutes, burning fuel and exposing the aircraft repeatedly to the heavy defenses of Iwata, but the bombardier was unable to drop visually. By the time of the third bomb run, Japanese anti-aircraft fire was getting close, and Second Lieutenant Jacob Bisser, who was monitoring Japanese communications, reported activity on the Japanese fighter direction radio bands. Sweeney then proceeded to the alternative target, Nagasaki. It too was obscured by cloud, and Ashworth ordered Sweeney to make a radar approach. At the last minute, the bombardier, Captain Kermit K. Behan, found a hole in the clouds. The Fat Man was dropped, and following a 43-second duration free fall, exploded at 11:02 local time, at an altitude of about 1,650 feet. Because of poor visibility due to cloud cover, the bomb missed its intended detonation point by almost 2 miles. Damage was somewhat less extensive than that in Hiroshima. An estimated 35,000–40,000 people were killed outright by the bombing at Nagasaki. A total of 60,000–80,000 fatalities resulted, including from long-term health effects, the strongest of which was leukemia, with an attributable risk of 46% for bomb victims. Others died later from related blast and burn injuries, and hundreds more from radiation illnesses from exposure to the bomb's initial radiation. Most of the direct deaths and injuries sustained from the bombing were munitions or industrial workers. Mitsubishi's industrial production in the city were also severed by the attack. The dockyards would have produced at 80% of its full capacity within 3 to 4 months. The steel works would have required a year to get into substantial production. The electric works would have resumed some production within 2 months and been back at capacity within 6 months. And the restoration of the arms plant to 60 to 70% of former capacity would have required 15 months. The Mitsubishi Urakami Ordnance Works, the factory that manufactured the Type 91 torpedoes released in the attack on Pearl Harbor, was destroyed in the blast.